In this presentation, the main topic of my presentation is essentially an analysis and a discussion of all the main issues, all the main problems that we have that are involved in the statistical treatment of the forecasting of solar proton events, especially through machine learning approaches. This is a brief outline of the presentation. I will spend a few words about solar proton events and in the framework, in the general framework of space weather forecasting. And then I will move to a specific model for the solar proton event forecasting, that is the Esperta model in this case. And I will explain the model and investigate all the problems that are related with the model and with, in general, this kind of dealing with this kind of data. And I will go through the model calibration and also the model validation. So as an introduction, I'd like to to report here an earliest definition of the space weather that is essentially the set of conditions of the sun and the solar wind, magnetosphere, ionosphere, and thermosphere that can influence human activity, basically, and human health. So in this case, we know that solar energetic particles are really important because are really hazardous for both human activity and human health. And solar energetic particles, just a few words, as Charlotte just mentioned them, and as everybody knows, are essentially composed by mainly protons and electrons, and in a minority part by EV rays. And they are sporadically emitted at the sun and associated with transient phenomena such as big solar flares and coronal mass ejections. They are detectable as sudden increases in, for instance, the proton flux, as called also solar proton events. And they are detectable in space and also sometimes at the Earth when we deal with relativistic proton energies, such in the case of ground level enhancement. Regarding the effect, essentially, of these solar proton events on human activities, I reported here just a few examples. They can induce, for instance, damages to spacecraft operation and electronics. They can affect radio communication, radar systems through the ionization of the atmosphere, and also be hazardous for the human health if we think about astronauts, operations on the International Space Station, and also pilots of airlines, especially during GLE events. So for all of these reasons, it's really important to have a good model, a robust model in making prediction of this kind of event. And we have many models that have been developed during the last decades to do that. And they can be divided essentially into these three classes. We have physics-based models that are computationally expensive in general because they rely essentially on the physics of the solar energetic particles. So we are putting the physics in this model, and this limit essentially the ability of this kind of model to produce a real-time alert. On the other hand, the empirical models and also the machine learning models that, let's say, can be considered a special class of empirical models do not deal with essentially the physics of the acceleration of particles, but just are a model meant for finding correlations, associations between some input variables, some proxies, like solar flares characteristics, coronal mass ejection characteristics, and find an association with the occurrence of solar energetic particle events. So these models are typically give a rapid forecast, and for this can be easily incorporated into an operational framework of space weather. The machine learning models rely especially on machine learning sophisticated technique, and we can say the same thing of the empirical models for them. So all of these models have to be constrained, of course, to the sun to earth transit time of the protons, that in the range between 10 MeV and 20 GeV is about 15 minutes up to a few hours. So just to have a look of how many models have been produced by the scientific community during last years, I reported here this table that classifies into these three classes all these solar proton events models. And just to compare some performances from this model, I find here the probability of detection, validation measure, and the false alarm rate that are quantifying essentially the goodness of our model in a predictive the positive event and how many false alarms our model is claiming for a given input. So these are some models I reported here, for instance, the POD and the FAR for all of them. And we can see that, for instance, if we look at this force path CME data and UMASEP, we can see that these models on difference with respect to the other include, for instance, the CME parameters as an input feature to make a prediction. We can see that the probability of detection increases in this case, but it's not the same for the false alarm rate that is not so much reduced. This is due to the fact that there are many fast traveling CMEs that are not associated with an SEP. So moreover, the CME observations are not available in real time. So another important quantity that we have to take into account when validating the model is the warning time. And I report here a nice picture of a solar energetic particle event observed on January 2016. And these vertical lines right here are essentially all the warning times associated with all of each of these models for evaluated on this event. So we can see that the ML soil LASCO models that rely essentially on coronal mass ejection precursors have a nice warning time. The last one to give the alert before the onset of the event is the UMASEP model that includes as an input feature also the proton flux itself. In this case, the Esperta model was quite delayed with respect to its average warning time, that is of more or less 4 hours. And this is due essentially to this smooth rising phase of this particular flare. So coming to more specific, let me focus on the empirical model for solar proton event real-time alert, let's say Esperta. And this model is essentially a model meant to classify and predict solar energetic particles in terms of binary classification, so occurrence or non-occurrence of the event, and by essentially using as a precursors only the flares the characteristics of the flares of class greater than M2. So the data set that we use in the validation of this model consists essentially in all the flares observed greater than M2 observed in this period of time, so between 1995 and 2017. And in this time interval, we have 92 number of SEPs event and a total number of flares that is 934. So from these two numbers, we can just fix some points of our discussion. So we are dealing with poor statistics, and we are dealing with imbalancing between SEP events and non-SEP events associated with flares. So the input parameters of the Esperta model are the flare longitude, the soft X-ray fluence, and the radio wave fluence. And I reported here the histograms divided by the classes, so associated to SP events and non-associated to SEP events. And we can see that the red lines that represent essentially the percentage histogram of the flare associated to SEP are essentially shows in longitude this very well-known asymmetry due to the fact that, as Charlotte said before, the Earth is well connected with the central meridian and western part of the Sun hemispheric equatorial region. So also solar X-ray fluence and radio waves are essentially good parameters in separating the two classes, the non-SCP and SCP associated events, but all this overlap region between all distribution that you are looking in this picture represent essentially a source of error for our predictive model, and thus they are uncertainty for the model. So if we look at this, if we look at this distribution and we evaluate the cumulative distribution function for both the SCP associated event and no SCP associated event, what we get is that for the SCP associated event, we observe a clear break here in correspondence of this value of the longitude, essentially associated with the fact that we are not well connected from a magnetical point of view along the Parker spiral with the eastern part of the Sun. And this allows us also to make a filter of the data. We can disregard Isner flares in an operational point, from an operational point of view, in order to make predictions for SCP events that are more important and more intense. On the other hand, if we look at the trend of the cumulative distribution function associated to the non-SCP events, we can see that there is clearly an independence on the longitude, so it is uniform. So Esperta, from the machine learning perspective, is considered a supervised learning approach, and we can indeed, in this framework, define the so-called feature input vector, that is a vector containing all the features, so all the parameters associated to the solar flares, and we define T as a target vector, a target variable. This target variable should be, in this case, is defined as a binary classification. So it could be 1 if it is 1 if the X feature is associated with an SCP, and is it 0 if otherwise. So we can define a function f that relates essentially the X features to the target variable through these weights that are still unknown at this point, and this is essentially this allows us to training the model, because by optimizing a neuron function, we can find essentially the optimum weights that allows to generalize the prediction to unseen data. So we use, in general, in the training phase, a vector T of known events and try to generalize the optimized weights to make new predictions. So the Esperta model exploits the logistic probability, so is a probability approach, in the sense that there is a probability function that is defined, is associated with each event, and the optimization is performed with respect to the log likelihood function. And the output of this logistic probability is mapped into a binary class. So we claim an SCP event if the probability associated to the feature X with I, for instance, exceed the values 0.5, or vice versa. So the main problem associated with the statistical treatment of this kind of data are essentially the overlapping, as I said before, of the SCP events and no SCP events in the parameter space. So this means that essentially looking at the parameter space, we have the classes that are not very well separated by the parameters. And this is due essentially to the, for instance, the presence of hidden variable that we are not considering, or the synergies between the feature in the model. So this framework, in this framework, this can induce a bias in our estimation. So in order to take into account this bias, we have to set a threshold right here, a decision threshold, and we have to optimize in the calibration of the model this decision threshold on the given dataset that we are studying. Another problem is represented by the imbalanced dataset, since we have a ratio between the SCP associated events and no SCP associated events that is 0.1. About 0.1, and in this case, if we look at the loss function, that can be divided into L1 and L0, where L1 is the loss function associated to the class of SCP event L0 is the loss function associated, the part of the loss function associated with the class of the non-SCP events. So we can essentially, we have two ways to balance the classes in the validation of the model. And these two ways are, the first one is the straightforward weighting of the loss function. That means that we are multiplying these two terms by the inverse frequency of the occurrence of the respective class. And the other things that we can do is essentially the oversampling. Oversampling means take the minority class and just generate synthetic data in order to augment the statistics of this class and to balance the whole data set. So after that, we have to validate our model, and I define here, these are the two metrics for the validation that I defined at the beginning, so the probability of detection and the false alarm rate, and these are optimized in this framework. These are optimized by finding the best trade-off through the so-called critical success index that is defined like this, and essentially is the index is the score associated to the model that maximize the probability of detection and minimize the false alarm rate simultaneously. And the validation of the model is done in the framework of stratified validation, stratified cross-validation. That means that essentially we are dividing our data set in different folds, and we are considering all the parts of the data set as a training set and as a test set. As you can see here, all the points of the data set are used to do this. So this allows us to give unbiased estimation that does not depend on the particular choice of the testing or training data set. In this case, it is important to note that in this scheme, essentially, I'm reporting, you have to think about this horizontal bars as the sorted data. And you can think that if we take the ratio between the length of these segments, for instance, in red, that represent the percentage associated to the test set, or in blue, that represent the percentage of data associated to the training set, the ratio between the two classes of these four sets is essentially the same. This is really important in the model calibration. So why this is important? Because if we perform a parametric study of these metrics, like the probability of detection and the false alarm rate, we can see this behavior, this different behavior. So in this picture, I report this figure, we have the number of layers in the train set on the x-axis and the number of SCP events on the training set on the y-axis. What we get is that if we change this number, so if we change essentially the percentage of SCP events that we are including in our test set, the probability of detection is almost unaffected. So we can see that the value is quite stable for all the values of the parameters. On the other hand, if we study the false alarm rate, what we can see is essentially that there is a strong dependence on the values, on the fraction of the SCP events that are considered in the test set. And we can, by defining tau as the occurrence of the SEP in the SCP events in the test set, we can essentially extrapolate this linear relation that for a fixed tau, fixed values of tau associate different values of the false alarm rate score for the same model. So this means that we actually have to choose a value of tau that in our case is close to 0.1, and it must be calibrated with the expected occurrence for the event, for the class of event that we want to predict. Okay, this is just an example. From a probabilistic point of view, if we write in terms of condition probability, the probability of detection and the false alarm rate of the model, what we get is essentially that the probability of detection can be considered as a simple prior probability, whereas the false alarm rate, after some math by applying the Bayes theorem, can be written in this form. So this means essentially that we can see here clearly that this explicit dependence on the ratio of the occurrence of SEP events in the test set, so in our data set. So the first important result of this analysis is that the model needs to be calibrated with respect to the occurrence of the solar proton events. During the model calibration, in order to do the validation of the model, we have to fix this tau that in our case is essentially 92 over 934, so is the ratio of SCP event with respect to the total number of flares included in the dataset. And for each value of the threshold, we compute the validation matrix. So in this case, we are essentially we vary essentially the decision threshold epsilon that I introduced in order to that I introduced before, and the optimal threshold minimizes the critical success index. This means that we are essentially choosing the best trade-off between probability of detection and false alarm rate. So you can see an important result from this analysis is that the parameters, the metrics of the validation for this model strongly depends on the value of the decision threshold. So we can see that there is a huge variation of the values of the score as a function of epsilon. So in this case, I reported here with these vertical lines, essentially for the three cases of basic Esperta, let's say. The Esperta with the weighting of the loss function and the Esperta with the oversampling of the minority class are reported here, the lines corresponding to the point of the maximum of the critical success index score. By looking at numbers, we can see that in this table, there is a comparison between the basic Esperta model, the Esperta model with weighted loss function and with oversampling. And we can see that the performance of the model in terms of probability of detection and false alarm rate is not changing so much. And the same can be seen also for by filtering the data, so by disregarding the eastern events, the eastern flare events. In this case, we can see exactly the same thing. We have an improvement of the performance of the model by filtering the data, but when we deal with unbalanced data, we do some weighting of the loss function or oversampling, we cannot see so much improvement in the performance. So this means that as a third result, I'd like to say that techniques for handling imbalanced problems do not get much better performance. This means, in conclusion, that this kind of prediction based on solar flare precursors essentially suffers from systematic error, let's say. So the phase space is not totally divided by the features that we are using as input, and maybe due to the fact that there are hidden variables or synergies that are not catched also for the low statistics of the problem by the machine learning approach. And we know that increased performance for longitude that are associated with flares of central meridian or the western part that are the well connected with the Earth are also the most hazardous. So in an operational framework, it makes sense to disregard the eastern part of the flares, because these are the most hazardous, having the fastest solar proton event onset, rise time, and peak intensity. So I leave here my conclusions, and I like to thank you so much for your attention.
Thank you very much for these highlight insights into a real topic of the forecasting. We have time for questions. Yes, Robbie?
Thanks for the very interesting talk.
Thank you.
I have an easy question following and a more complicated one. The easy one is, do you see any differences in solar cycles, in the success rate for positive or negative solar cycles?
Okay, so in this case, we actually didn't divide the class of event in solar cycle, in different parts of the solar cycle. But all this kind of information, in some sense, are present because we are considering all the solar flares of a class greater than M2. So the information of the solar cycle, the solar activity is essentially contained in the occurrence of flares, in some sense. So this kind of information are present in the model, but we didn't do that because we want find a let's say, an effective and robust statistical way to treat with predictions. It's not physically based.
It would just be interesting to see if the predictions are of equal quality depending on the solar cycle.
Yeah.
The more complicated question is this. Machine learning is computationally very expensive, at least quite often. So my question has always been, why does one not use physics in machine learning algorithms? We know physics works. We know the physics, and that's a fact. So why do we let a stupid machine try to learn physics on its own? Why don't we give it that?
But physical models are expensive. If machine learning models are also expensive from a computational point of view, to bring them together could be a little problem. No, in this case, I'd like to answer like this. In this case, we are not dealing with expensive machine learning computations. So this is just a classificator. So we are dealing with a few data points in terms of hundreds. And this allows us to have a quick prediction and instantaneous prediction by knowing the flares characteristics. So in this sense, this kind of model are not expensive from a computational point of view.
I think there is work going on into that direction, especially in putting in the modeling of the evolution of the magnetic topology on the sun, and then going on.
That means start including some physics.
Yes.
In this kind of
one last question. You mentioned the three approaches, and from the concept, is the machine learning approach better suited for short-time warning times, or is there, you mentioned up to 2 hours?
Yeah. It depends essentially on the event, because you are constrained essentially to the physics of the events that you're looking. If you see this slide, I reported here, for instance, this constraint that is essentially general for all the model, both physics-based, empirical, and machine learning. So.
Yes. Okay. Thank you. More questions? Doesn't seem the case. Also, remote, we have no questions. So let's thank Simone once again.
Thank you.